Welcome to the explanation of the task overtaking from IOI 2023. In a moment, I will explain to you what the task is about, and then I will bring in my friend Zsolt, a professor here at LT University, who will help us understand the algorithms behind the task and will actually get you to know more, to learn some things, and to be able to program it. And Zsolt always says, just sit down and program it, and that's what we'll do after the explanation. Right now, I want you to go to our website, download the task, and read it first. So pause this video until you've read the task, and then come back here and we'll continue. The task overtaking that you've just read about is a task about buses traveling on a single lane highway where they cannot overtake one another, they can't pass each other. So a slower bus will hold up the faster buses that are coming behind it. But on this highway are various points that are called passing stations, sorting stations in the task. And at those places, buses can overtake one another. So at each sorting station, what happens is all the buses that are in the queue at that point, that are all stuck behind that slow bus, get rearranged so that the fastest bus goes first and the slower buses come after that until the slowest bus is the last one behind there. Now, because this is an algorithmic task, you don't have to worry about the length of the buses or the width of the buses. They're just points on the line. If I look at my screen here, the buses they can travel a certain distance and it will take them a specific amount of time to travel that distance. So here I have a bus that takes 3 minutes to travel 1 kilometer. So if it starts at kilometer 0 after 2 minutes, it will be at kilometer 10 30 minutes later. So at time 32 minutes. So this is what one bus will do. No interference from any of the other buses. It gets a bit more interesting because if you have a faster bus, where the angle here would actually be less because the bus does more kilometers in one minute, this bus will catch up with that slow bus and then will get stuck behind it. So even though this bus leaves later, but is very, very fast, it could have arrived much earlier, but because it gets stuck behind the slow bus, it still ends up at kilometer 10 after 32 minutes. If I put in some sorting stations now, it gets even more interesting. You can see here that the bus that leaves at time 10 is a fast bus. It catches up with the slower bus and it has to stay behind that bus until the next sorting station. As we've seen before, at the sorting station, the buses get reordered and the fast bus gets to pass and will actually end up a bit earlier at the 10 kilometer mark. So faster buses get there earlier, slower buses get there later, and at the sorting stations, the buses can pass one another. Now what's interesting about this task is that you are given a whole bunch of buses that are traveling, and you're told where the sorting stations are. So at how many kilometers away from the starting point are the sorting stations. And this task is about an extra bus that you want to get going on there. So the extra bus will have to fiddle in with this chart. So here I have a chart with 4 buses and they are all driving a specific speed. They leave at a specific point in time and you can see they sometimes catch up with one another. They sometimes can pass one another. Sometimes they can't because they catch up with the slower bus after the last sorting station. And we see here at these departure times at what time do the buses arrive at the final destination. Now let's add in one bus that we're asking a question about. So I have a bus here that's a very, very fast bus. And you see it catches up quite quickly with the first bus, with the light blue bus. It has to stay behind it until the next sorting station. It quickly moves on. It passes it, quickly moves on, and then it catches up with that other bus, but way beyond the last sorting station, so we can see exactly at what time the bus ends at the destination. Now you may think, Kim, what's hard about this? This is just simulation and we can do this easily. And that's true, obviously, but what we will be doing is in this task, we will give you the fixed set of buses and sorting stations, and we will ask you many, many questions about buses coming in. So what you're trying to do is find a way to optimize giving the answer. So the question is, if a bus with this speed leaves at this time, at what time will that bus arrive at the destination? So that's what we're looking at. And so you see all the buses. So we have now, to start with, just a single bus going and an infinite amount of sorting stations. So if we add one more bus, there are a few things that can happen. If the extra bus is a slower bus than the bus that's going, then that slower bus doesn't really suffer at all from the bus that's already going. Because it may just go in one go to the destination. It could also be that it holds up the bus that is already there, but our slow bus doesn't suffer at all. So if the bus that is already there drives faster than the bus that you're trying to add, the bus that you're trying to add will just arrive at its normal time at the destination without having suffered anything at all from that faster bus that's there. If the slower bus leaves later than any of the buses that have left before it, then obviously it will never catch up, and also, it will just arrive at its destination without having suffered at all. Now let's make it a little more interesting and let's have a faster bus go. It gets more interesting if the bus that we're trying to have drive now is faster than the bus that's already in the schedule. If this faster bus leaves earlier than that bus, there's no issue. You can just see that faster bus just arrives at the destination without any delay. It doesn't have to overtake the slow bus. But if that faster bus leaves after the slow bus, it can be the case that it needs to overtake that slower bus. For instance, here it leaves slightly after the slower bus, and you can see that it catches up quite fast with the slower bus, and at the first sorting station, it overtakes that bus, and then it continues on and doesn't suffer much more. It could also catch up with that slower bus slightly later, as you can see here. So here it catches up after the first sorting station, but before the second sorting station. So it has to just drive along with the slow bus until that sorting station, and it will overtake it right there. And obviously, if it leaves even later, it could catch up after the second sorting station. Boom. And then it will never pass the bus. It will just arrive at the destination at the same time as the slower bus. And as you can see, if it leaves even later than this, it won't suffer from that slow bus. So this first subtask is actually not that hard. If the bus that you're trying to put into the system is slower than anything that's also already in the system, and there's only one bus already in the system, if it's slower, then you don't have to worry about it at all. It will just reach its destination at the normal time. Now, if it's faster, as you've seen, you have to find out if those two lines intersect. Finding an intersection is not that hard to do. All you need to do is do it once, because there's only one bus you're putting in there and there's only one bus that's already in the system. Once you have the intersection point, you know how many kilometers away that intersection point is, and all you need to do is find out, is there a sorting station after that intersection point? And you take the first sorting station, and from there you let your bus continue on to the final destination, and you know the time that it arrives there. And if there's no sorting station after the intersection, then obviously the bus arrives there at the same time as the slower bus that's already in the system. Now, it gets much harder if you have more buses in the system and many more questions that are being asked. So for that, I will bring in my friend Professor Zsolt from LTE University in Budapest. Welcome, Zsolt. We're now going to look at subtask 2, where there will be no sorting stations, but many buses and many questions being asked, right?
Yes, exactly. And solving this subtask is also crucial for moving on towards the full solution. Because actually, if you think about it, beforehand we were just talking about having lots of buses who go from the initial station to the final station, interfere with each other, and so on, change trajectories. But actually, you somehow need to compute and maybe even store it on your computer. Your program has to somehow come up with this from the times the buses leave and the speeds of the buses. You are on your own.
And the reason we have this subtask is because between two sorting stations is basically the same problem, except with no sorting station, because you have starting times of all the buses that leave the sorting station.
Yes.
And you want to know the arrival times at the next sorting station or at the end. So we're actually making the problem a little smaller, but it's a problem that you need to be able to solve in order to solve it for everything.
Exactly. So this is a typical case when the subtask tries to help you with moving on towards the full solution, of course.
And this is important for the people at home. So you may want to think about this a little bit before you continue watching us, because what we've just done is we've broken down this really complex problem into smaller problems. What happens between the sorting stations? And the subtask says, you only need to look between two sorting stations because there will not be any sorting stations. So it's just start to end. So let's take us to it. What are we going to do? Let's start with an empty chart, I presume.
Yes, exactly. So somehow we need to process all of these buses. And what we are going to do, as it comes naturally, is to deal with them one by one. Now you have to come up with an idea how to deal with them one by one. You can sort them somehow, sort them by speed, by time, whatever you would like to. But here for this subtask, probably the most natural idea is to sort them by the time they leave the initial station.
Okay.
So let's just look at an example. This is the first bus that leaves the initial station. It arrives at the second station at some point. The next one leaves and then arrives.
It's a slower bus.
And you can see it's a slower bus that left later, so it arrived later. Yep. But now let's look at a bus that leaves later, but it is a faster bus. So in this case, it gets stuck behind the slower bus until the next station.
But now my core question obviously is, to find this, do we look at all the previous buses that have left? Or do we only look at the last bus? What do we look at?
So yes, that's what we want to optimize, because the worst way you can do it is if you look at all the previous buses. That will take a lot of time because you have n buses, let's say, then you have like n square comparisons between them. So we need to somehow optimize it. And you have to be careful because it can happen that, for example, the blue bus catches up to this cyan bus and they arrive together. But maybe some bus that leaves later catches up to the blue one first, and then they both catch up to the very slow cyan bus.
I feel a core insight coming now. I feel something, and we've looked at this before, but there's something very important coming in now regarding the green bus, which buses we should look at.
Yes, because you can see that it does not matter how these buses group up until the point they all end up behind the cyan bus in the end. So somehow we want to find all the buses that get crammed up together and arrive at the same time at the sorting station. And for that, the main insight is that it is enough to compare all of them to the cyan bus and don't compare them to each other. We don't care if the green bus catches up to the blue one, because in the end it will catch up to the cyan bus.
And so that's the core insight. So the core insight is you don't need to know about every bus catching up with every bus where. You just need to know the slowest bus that it caught up with to get here. And everything else you can forget. So orange catches up with cyanide, blue catches up with cyanide. So we don't need to compare green with blue because we know blue got caught up with cyanide. So green, if it catches up with blue, it will definitely catch up with cyanide. So we only compare green to cyanide.
Exactly.
Okay.
Yes, that's what we are going to do. That's what we are going to do. So we will always have one active bus, the last one, which actually arrived at the second station without any interference with other buses. So this time it is the cyan bus that is the active bus to compare other buses to. And yeah, the orange one gets compared to it, it gets stuck behind it, and it means that for the later buses, we actually disregard the orange bus.
We forget about the orange bus.
Exactly. So for the blue bus, we don't care about the orange one, though they don't even meet. And the blue one catches up to the cyan bus. So it means two things. The blue bus will arrive at the same time to the second station, and we can disregard the blue bus from now on. So originally, the green bus caught up with the blue bus, and then together they caught up to the cyan bus. But now we just compare the green bus with the cyan bus, the last active bus. And since they get grouped up, they arrive together.
And that's the core insight, even though your picture here is slightly wrong, because it's not what will happen to the green bus.
Yes, it's not the reality.
The picture between here and here is exactly what will happen to the green bus.
Yes, so this is what your program should do.
Right.
It's not what happens in reality, of course.
Okay.
So actually we disregard the green bus from now on, but at some point we may get to a bus that starts from here and arrives at the next station without catching up to any other bus. That means that instead of the cyan bus, now this deep green or dark green bus will be the one to compare to.
So this is really cool. So this is really clever, and the subtask is trying to help you with this. So what we're trying to say is, forget about the stuff that's not necessary, and basically all we need to do is sort stuff here, and then analyze whether we'll catch up with something, and that we can do just by seeing if the lines cross.
Exactly. So after sorting the buses by the times that they leave, we always have one active bus to compare to, and that can be done very efficiently based on the first subtask, for example. So in this task, we will get a bit into like asymptotics, how much time it takes, how costly it is to do certain things, because it is a simulation task. And the main idea or the main thing about this task is to do things efficiently. So let's try to think about how efficient it is. And it turns out that since we only need to sort the buses and after that iterate over them once, it takes n log n times maximum.
Right, and this is for one simulation.
And this is for the simulation from one station until the next station.
And just answering one question, because what you're saying is, just throw that question in there, simulate everything, n log n is not an issue, but we have many questions.
Exactly, but since we started talking about the second subtask, in the second subtask, we only have the starting station and the final station. There are no sorting stations in between. So it turns out, if you just look at the constraints of the subtask, that you can do this simulation for each and every question. For each and every question, you can start from scratch. You have n buses, add an extra bus, the bus in question, simulate everything and answer the question and move
within
on.
the time limit.
So you have to do this.
I see a queue appearing somewhere.
Yes. So you have to do this queue times.
Okay. So this is very doable. So this is subtask 2, right?
Yes.
So subtask 2 is very, very doable. Do we move on to subtask 3 immediately, or are there more key insights?
Yes, because if you are doing the task this way, then you can immediately move on to the next subtask where you actually don't need an extra idea. You just have to extrapolate it to multiple sorting stations. So you just have to realize that if you got from one station to the next one, then at the next station you can initialize a new step, a new segment to simulate by taking all of these buses and release them from the correct times.
Right, so we basically resort everything and we just use this as our new starting point.
So we just have to know which buses were inactivated, which buses were disregarded at a certain active bus, and then sort them and release them from this common time.
So we do the same thing multiple times. We just
Yes.
have to keep track of this, and it's already sorted, basically. We just need to sort
Yes,
here.
so this subtask is about coding it
Yes.
efficiently, and you have to add some extra steps. I mean, you have to, because for the previous one, you didn't need to store or keep a list
Right.
or whatever of these buses, sorry. Now you have to keep tabs of these buses, sort them, do some extra
Right.
steps, but
it's understandable.
yes, understandable, and yeah, from the theoretical point of view, you just do the same thing m times if you have m segments here.
And then if you have Q questions,
Yeah, then you can do everything from scratch, from the very first station, adding an extra bus and simulate and answer the question.
and so the constraints for subtask 2 and 3 are given so that if you do it this way, you still score the full points for those subtasks.
Exactly, because in these subtasks, the number of questions were bounded by a number that allows this.
Right.
So what we would like to do from now on is increase the number of questions gradually, so we cannot do the same, and we have to come up with some idea to add the extra bus without recalculating everything from scratch.
Right. So that is your task at home now, is to pause the video and think about, can you improve on this? Which data can you store? Which data can you reuse so that you don't use this much information to solve this problem? And we'll do that in a minute with you as well. Let's look at the fourth subtask of the overtaking task. Zsolt, walk us through it.
Okay, so in the previous subtasks, we only dealt with the idea of how to simulate the whole process, and you could just simulate for every question from scratch. So, of course, to move on for a big number of questions, we have to find out a way to quickly find the answer for a single question.
Right.
So, how to do this? Let's suppose that we have the n scheduled buses, and we already computed the previous structure. We already know which bus leaves which station at which time, with how they cramp up, and so on. So let's say we want to add a bus later on when we have a question, for example. So, for example, this bus leaves the first sorting station here and would go with some speed. So it meets with multiple other buses. There are two buses that will be crammed up behind this. These two fast buses will be behind this slower bus. And this slower bus catches up to an even more slow bus in the end, and they arrive together at the end point. So it turns out that from these three changes in the trajectories, two are irrelevant and only the last one is relevant. Because when the faster buses catch up with the slower bus, it won't change the trajectory of the slower bus.
It will change the dark blue line or the pink line, but not our bus's line.
Yes, exactly.
Because it's a faster bus. We already saw, I think.
As we discussed,
subtask 1,
yes, in
faster
subtask
buses.
1, it was the main observation.
Yes.
Only a slower bus can change the trajectory of a faster one.
Okay.
Yes. So this is the only relevant change with respect to the bus in question. Okay, here the image, the picture is a bit misleading because, these two get hauled up, but they will still arrive together to the next sorting station. So you may also ask what happens if the trajectory changes such a way that the blue bus would actually arrive together with the slower bus at a later point of time.
Right.
Can it cause any issues? No, this is still not relevant because the faster bus changes trajectory.
And the faster bus here would go out at a lower angle, so there's no way we'll
So
ever
there's
catch up
no
with
way
that.
to have any interference later on.
We really don't care about fast buses.
Yes, and we also, since all of these intersections, all of these meetings are irrelevant, it turns out that once again, the only relevant question is if this new bus meets with the active bus.
Right, in the
From
simulation.
the previous
yes.
subtest, from the simulation. So it turns out that over the simulation, we have to keep track of the active buses and use those over the simulation. So how to simulate it? We will go over each segment Okay, of course, first of all, we simulate everything. We store for each segment the active buses and so on and so forth. This preparation step takes n times log n, as we already discussed. And now, when adding a bus, we just simulate the process by starting from the starting point, find out the last active segment that is the last active bus that left before the current one, and figure out if they meet and get here together or they don't meet, and then repeat for the rest of the segment.
So we need to be able to figure out in a smart way what was the last active bus that started at the specific sorting station or the starting point?
Exactly.
Before
yes.
Okay.
But remember that over the simulation, we processed these buses in the chronological order.
Right.
So we already probably have them sorted, so we can just binary search it or query it from a data structure.
Okay.
So yes, at each segment, we have to find the last relevant active segment that takes log n time, because we may have at most n active segments. We do this for every segment between every 2 consecutive stations.
Right.
So to simulate the process for a single bus, it is m times log n.
And so the smart thing we've done here is we do the setup. Because originally we had ONMQ log n, so that Q was in here. And now what you're saying is, no, if we just we do the pre-calculation without the question bus, then it only takes this much time. And so Q can get really, really big.
Yes, so here you can increase the value of Q quite a bit because you got rid of an n factor.
Right.
Though still Q times m can be a bit too large. So we still have one last subtask to do and optimize it a bit further.
Ooh, good. So we'll do that in a second. So at home, think about this, see if you understand what we're doing here with the pre-calculation and then the questions, and try to think if you can come up with the same solution to improve it even better. Now for the last part of this task, we're trying to allow even more questions before we run out of time. So in our formula, we saw that basically QM log n is how much time it takes, and the questions are given to us consecutively, one by one, so there's nothing we can do there. But we're going to see if we can come up with a smarter data structure so we can move the m inside the logarithm. That's the next trick, right?
Exactly, you are right, because, previously to answer any question, we iterated over all of these intervals between the sorting stations. Right. And you may have the idea that maybe we can optimize it somehow to not have to do it anymore.
Well, the natural way that I was thinking about this is that there are probably a lot of buses that end up at the same time because they all catch up with the same slow cyan bus. So I think that's what we're going to look into next, right? How can we group buses together to the same time?
Exactly. So that's what we are going to do. We are trying to somehow simulate the process for any possible starting time for the extra bus and store it somehow, and when a question comes, find the answer. So yeah, let's consider some starting configuration, and remember that there is one detail that we haven't really used in this task yet. The detail is that the extra bus, the new bus, always have the same speed.
Ooh, so every question that will be asked about a bus will be asked about the exact same speed. So we can do a lot of pre-calculations now for that specific speed.
Exactly, yes. So what we will try to do is we will look at the possible starting times of the extra bus and try to simulate, try to think what can happen for different starting times. It is obvious that it is important if a bus leaves before or after another bus. So initially we could just consider the intervals determined by the original n buses. And of course, we can use our previous data structure as always, which keeps track of the active buses and disregards the
so we don't have to care about
buses.
the non-active buses.
Of course,
okay, fine.
That will be reused, this idea. Okay, so let's start with this first segment where you can see that a relatively fast extra bus would go uninterrupted from the starting point to the next sorting station. So basically, no matter from which point it starts from this segment, it will end up at a corresponding point at this other segment.
Right.
So basically, this segment gets projected to this segment.
It's a direct projection.
Yes, exactly.
If you start in this segment X minutes after the beginning, you will end here X minutes after the first point in that segment. Okay.
Yes. Of course, this is not always the case. For example, if we move on to the next segment, here at the very first point, we would immediately get caught up after behind a slower bus. And even later on, even if we start at the very last time point, we will still end up stuck behind this slower bus. So we would end up at this point, no matter what happens.
Right, so this whole segment maps to a single point, a single time. Everyone that starts in this segment gets there.
Yes,
okay.
Exactly. Okay, and there is one more case, because it's not always the case that a segment becomes a segment or a segment becomes a point. Sometimes both can happen at the same time. So actually we can consider the rest of the points together, because this bus here is faster than the query bus. So we can disregard the faster bus as we previously observed. Oh, yes. So for this segment, from the starting point, we actually catch up to a slower bus and end up at this point. So we know that there is one point from which we meet a slower bus.
Yes.
And later on, there are points. It is always enough to check the end point and maybe add a dummy point at infinity.
So I'm working my way backwards from this point. Mm-hmm. Basically, if I take the road backwards, if I look backwards from this speed, I can find out anything above there is the segment, and anything below it maps to that specific point.
Exactly, and it is possible to do this at this exact moment. So you could just try to figure out what is the smaller segment that gets projected to this point, and then deal with the rest afterwards. What we are going to do here, we will switch things up a bit and first try to imagine what can happen, okay, and then we will come up with the algorithm. So yeah, for an initial segment of points, those will be projected into this single point. And after that, there is a segment that gets projected to this other segment.
Right.
So these are the three possible cases. A segment may become just a segment may become just a point, or, this is the last case, a segment can become partially a point and partially a segment.
Right. And then we've done that for the first bit, and we go do it for the second bit as well.
Yes, and then it's essentially you get back to the starting configuration. Here you can consider the relevant segments or points and right, do it once over again. So this segment gets projected to this segment. Here, whenever you end up being a point, the point always gets projected right into a point. So this point becomes this point. And here we have a point plus a segment. And you can see here that this point will become a new point after the step. But also this segment, part of this segment will become a new point, and another part of it becomes another segment.
But a point never becomes a segment, yes, because once you're all converts to something, a point is that point, all the buses will have that time, so it will never become a segment.
Exactly.
So segment stays segment becomes a point, or segment becomes a point and a segment.
Exactly, these are the possible cases. And what we would like to do is what you already mentioned. At some point, either before or right now at the end, we want to figure out how to break the initial intervals into sub-intervals, so that we can tell exactly which points will be projected to a point and which points will be projected to a segment.
Right, the point segment thing we still need to break up, because there are actually two segments that come into that. There's one segment coming in going to the point, and another segment going to a segment.
Yes.
Okay.
Yes, and for that we can simply consider the points at the very end and move the bus backwards right until the starting segment. And since we arrived to this point uninterrupted from the start, we can go back right to the beginning this way and break up the initial interval, the initial time interval into subintervals.
And so here what you've done is basically say a bus that leaves in interval A will arrive always in this mapped interval A.
Yes.
A bus that leaves in interval B arrives at time B.
Yes.
Interval C goes to time C, interval D goes to time D, and interval E goes to interval E.
Exactly.
And they could alternate. There could be another point above that.
Yes.
Right? So you could have points and segments alternating.
Mm-hmm. Yes, okay. Yes. So any kind of combination can occur. And yes, the idea itself is kind of natural. We want to backpropagate all this information later on into the starting interval to answer the queries. But what is a bit, or what is not clear immediately is if we can do it efficiently, or is it efficient enough?
Right.
Because a segment can split into a segment and a point. So you may think maybe we will end up with a lot of segments and points and this is not efficient.
Right.
But the main observation regarding the complexity of this solution is that initially you have n segments. And
yes.
And the number of segments cannot increase. After that, you either have n or a smaller amount of segments.
Right. It either stays the same because it turns into a point and a segment, or it turns into a segment.
Yes.
But it never splits up into multiple segments.
Yes. And the other observation is that a new point can only be obtained from a segment.
Right.
Because a point always stays a single point.
Right.
So it turns out that initially we have n segments. After one step, we have at most n segments and at most n new points, because every segment can create at most one point. And after that, we still have at most n segments and at most n new points.
Right.
So at every sorting station, we can increase the number of points by at most n, and the number of segments cannot increase.
And we can do that m times.
Yes, so we have n times m points in the end at most. So it turns out that since running the simulation is still the same m times n times log n, and since in the end we end up with m times n points at most, the backpropagation also takes at most m times n or m times n times log n amount of time. So we can do all of this under the same complexity once more.
And now all we need to do is look stuff up here where we'll have m times n segments at the most.
Yes, that's it.
So, and Q questions, so bring it in.
So yes, this is the improvement. For every question, we just have to find the segment in which the point resides in. And to do that, we have at most n times m segments here. So we have to either binary search it or query it from a map or other basic data structure in a logarithmic time. So for every question, it is log n times m.
And so then the question is, people just have to sit down and code it.
Yes, and actually here in this problem, it's a bit tedious. It's a bit tedious. I don't know how much people are familiar with it. This task came to IOI 2023 as a backup task.
Right.
So there was another task which has similar ideas, but was a bit easier to implement. But since that task failed to make it to the problem set, we used this backup task. It's a bit more tedious to implement, but it uses similar ideas.
But it's pretty cool that the backup tasks at IOI are still of this high level and are still this interesting. Because the reason we disqualified the other task was because it was too similar to something else that had been used before. We did not disqualify it because it was bad.
Exactly.
And this is the level of our backup test. This is really good.
Exactly, yes. And actually we were very proud proud about this backup task in the sense that there were like no issues with it, like no fake solutions scoring obscene amount of points or any problem. So we are very happy about this task.
That was it. The solution to the task overtaking from IOI 2023. And as always, I've discussed it with my dear friend, Professor Zsolt, here at the University in Budapest.
Yes, thank you for coming and having this time together. I think it was very informative, or I hope it was very informative, and I had a good time.
It's always fun, right? I mean, algorithms are fun. So I hope at home you feel the vibe and the enthusiasm that we have for algorithms, and we'll be back with more movies.